In this video, we're going to look at graph theory. The graphs we come across in decision maths differ to anything that we've met in either a pure or applied unit. The first thing you'll notice is a lack of coordinate axis. So for example, if we were asked to draw the graph of y is equal to x, y is equal to cos x, y is equal to 2x, y is equal to x squared, the first thing we do now is have a set of coordinate axes. We've got x and we've got y. So let's draw the graph, for example, y is equal to sine x, and take x between 0 and 360. We come up, round, back like so, and that would be our graph. In decision maths, a graph looks something like this, or it could look something like this. So these are examples of graphs. In decision maths, a graph is simply a collection of arcs or edges and nodes or vertices. So let's look at those pieces of information. This is an arc or an edge. You need to be comfortable using both terms. So arc or edge. The little dot now is a node or vertex. The plural for vertex is vertices. So what we'll have now is a node. We can write that on node or vertex. If you like, these are simply now a collection of dots and matchsticks. Quite clearly you wouldn't refer to them in an exam in that manner, but that's what it is. We can use these graphs to simplify some really complex problems. An example might be the motorway system in the UK. All it is essentially is dots and matchsticks. So let's go ahead and try that. Let's go ahead and we'll do that. So what I'm going to do now is get this particular part here. So here is my node or vertex. Here's my arc or my edge. The node or vertex is going to represent a city or town. And then we're going to have the arc or the edge representing a road. So let's go ahead now and put another one on, and we can spin that round. So what I'll have is something looking like that, and then I'll put another one on. Let's put another one on. So what I could have done now is just modelled a part of the UK motorway system. So let's go ahead and let's say that this is going to be now London. So let's put London just here, and we might put now, let's say, Bristol just here. Okay, we've got London, Bristol, let's say we've got Cambridge just here, and let's say we've got Nottingham just here. So this now could be the M1, this could be the M11, and this could be the M4. This is an example of a graph. So I've got my arcs or edges representing the motorways, and the nodes or vertices representing the cities. In terms of the lengths of these, it doesn't matter in terms of what we're going to put on there. So for example, London to Cambridge is about 60. London to Nottingham is about 120 or 130. You will be given a value on these. The value is called the weight. So that's our new bit of terminology, the weight. Now this doesn't mean that one is heavy and one is light as such. The weight could refer to the distance in miles, the time in minutes, the cost in pounds. So these are examples of weights. What I'm now going to do is take this graph and turn it into a network. If I write down a network now is a weighted graph. So network is a weighted graph. So let me put some distances on in miles. I don't know, let's say that's 130. Let's say that this is now 60. And let's say that this is going to be, let's say 110. I don't know how accurate they are. They seem okay though. So what I've now done is turned my graph into a network by adding weights to the arcs. So if you're making notes, graph, nodes or vertices, arcs or edges, this is the weight, which is either the cost, the distance, the time or something of that nature. And then now a weighted graph is called a network. Okay, let's look at another new word. And this video is going to be filled with lots of new words. We're going to look now at what we call a subgraph. So let's write this down, a subgraph. A subgraph is simply part of a larger graph. Or if you want something more formal, if we take now the graph G, and let's call this G. Now in the subgraph, the nodes and the arcs are going to be part of the original graph G. So let's look at now a subgraph. So this now is the original graph G, and I might want to draw, for example, a subgraph. As you can imagine, we've got a whole host of different choices. So what we could say now is the following. I could say that A, B, C was a subgraph, and I could draw that. So if I wanted to draw that, all I would do is go ahead and simply spin that round. I would now put another one just here, and then I'll put another one there, and then finally I'll put one this side. So a rough sketch of that would look something like this. So this is an example of a subgraph. The nodes, or now vertices, and arcs or edges belong to the original graph. So if I wanted a different one, let's go ahead and do a different one. Let's say I had something that looked like this. So I might go up that way, I might do something like that, I might do something like that. So that again is a subgraph. Okay, let's look at 3 new words. The 3 new words all mean the same thing. That's order, valency, and degree. So order, valency, and degree. These mean the same things. All this means is with our vertex or our node, how many edges or arcs are sticking out of it. More formally, we say it's the number of edges incident to a vertex. So if you answer a formal definition, the number of edges incident to a vertex. So if we take now an example, what we've got here is a node or a vertex. And we can see at the moment it has a valency of 1, or degree of 1, or an order of 1. If I go ahead now and add another arc or edge to this, let's do that with that one, what we've now got is a valency or order of 2. If I added another one, we'd have now a valency or order of 3. So if we look at our graphs, for example, let's grab this graph back up here. We can go through and look now at the order of each of these vertices. So here we can see this has an order, valency or degree of 2. We can see this has got 3. We can see this has got 4. We can see that's 2, 3 and 4. So what we've got now here is the valency or the order or even the degree. I like valency. Later on we will look at the consequences of having odd and even valencies in our nodes. So if we, for example, if we've got 3, that is an odd valency. What I'm going to do is just consider something called the handshaking lemma. The handshaking lemma says that the total sum of the valencies is going to be double the number of arcs or edges. Now that kind of makes sense. If we just take this now, we can see if I add now to any graph an arc or an edge, it's going to add 2 ends. Therefore now the total valency will always be double the number of arcs or edges. So let's look at this one right here. If we look and said that this now was a graph, we've got now a total valency of 1 and 1, which is 2, yet we've now got 1 arc or edge. If we look at this, 2 plus 3 plus 4 is 9, 11, 14, 18. So we can see the sum of the valency, so the sum of the total valency now is 18. If we look at this now, we've got on here, if I take the arcs or edges, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can always see now that the number of arcs or edges is going to be half the total sum of the valency. And hopefully that shows you why. Each arc now adds 2 to the total valency. Okay, let's move on and look at a new definition. So if you're writing these down, here's another one for you. Let's take the definition of a path. A path is now a finite sequence of edges. These arcs or edges start and end at a vertex. Each vertex will only appear once. So let's look at an example of that. Let's grab this up right here. So what I've got then is my graph. So if we wanted to call this graph G, I'm now going to draw a path. So what we can do is the following. A path might be the path P, Q, R, T. That is an example of a path. As you can see, there are going to be a whole host. We've started and finished at a vertex, and we've not now gone back to any one of these vertices. So we can say now that this is a finite sequence of edges where each arc or edge starts and ends at a vertex, and those vertices do not appear more than once. So for example, if we were going between towns, we went from town P to Q, from Q to R, from R to T. We wouldn't now go back to Q from T. If we now move on, we can look at what we call a walk. A walk is very similar to a path, but we are allowed to go back. So if I now get up a graph, an example of a walk, let's do a walk instead of a path, and we could go from P to Q, Q to U to R, back to Q. So you can see now that I've been to Q more than once, and this is what differs. So path and a walk. Lots of our work later on will concern paths, and more importantly critical paths when we look at critical path analysis. So path, finite sequence of edges that now start and end at these vertices, and the vertex is not appearing more than once in our diagram. Okay, next definition is a cycle. A cycle is a closed path. So we've got a cycle, and we can say that's going to be now a closed path. So let's go ahead and look at a cycle. So if we grab this up, an example of a cycle might be, and we could choose, let's say we had Q, R, T, U, Q. So that is an example of a cycle. So if I wanted to do this, we could say that Q, R, T, U, Q is a cycle. When we look at minimum spanning trees or spanning trees, we will see that these trees cannot include what we call a cycle. So it's an important definition that you need to know. A cycle is a closed path. So we can see that this is closed off. And again, these are not necessarily exclusive. Okay, let's move on and look at what we call a connected graph. So what I'm going to write here now is a connected graph. So a new piece of terminology, connected graph. So let me now just make myself a graph from my nodes or vertices and arcs or edges. So this, for example, is going to be a connected graph. So let's do something. We don't have to make this elaborate. I don't have to make some new massively cool structure. And that's a graph, okay? And that now is a connected graph. Each of the vertices is connected. Now, if I went ahead and did, for example, this, that is not a connected graph. This is a connected graph. As soon as I include this part right here, it's not connected. As we can see, there's no link now between these two vertices, this vertex and that one. So that would not be a connected graph. Connected, not connected. Quite clearly, I can make this a connected graph by simply doing that. That's now connected. That's connected. Or if I wanted, I could just do this. That now is connected. So that now is a connected graph. Let's now look at the definition of a loop. So we got now a loop. A loop will start and end at the same vertex or node. So what we've got then is this, and all we'd have now, a loop can come round. It would start here and end here. So if this was vertex A, we can see that this is an example of a loop. So in a graph, you might see something looking like this. Let's draw a graph with a loop in it. Now, it doesn't necessarily have to just be that ring sitting by itself. You might have something that does, let's say we got this scenario. So this now is a graph, and we might have now our loop just here, okay? So this might be the loop, there's the loop, and we might have something else. So it doesn't, it's not necessarily independent. So it might be something like that. So that's an example now of a loop. So it starts and ends at the same vertex or node. Okay, let's now look at what we call a simple graph. A simple graph will not have any loops and no more than one edge connecting any pair of vertices. So let's see what that means. So this now is a simple graph. Okay, so a simple graph. And I'll show you what is and what isn't one. Okay, let's grab this up right here. So say we've got now, this is our graph. This is a simple graph. I've got no loops, and I've got now none of these vertices connected, the same two vertices connected with more than one arc. Yet as soon as I do this, it no longer becomes simple, as I've got, let's say this is A and this is B, I can see I can go this way or this way. So this is no longer a simple graph. Another example might be if I have, let's grab another one up, I could do this right here, and I could say, for example, that I'm going to have now a loop just here. So this is a loop. So I can come around here and Q can go this way round or it can go that way round. With the loops, I can go from A to A that way round or that way round. And this is not a simple graph. So simple graphs have no loops, and each arc now, or I should say each vertex or node, doesn't now connect to another in more than one way. Okay, let's move on. We're now going to look at what's called a digraph. So let's write digraph. Digraph is a directed graph. So if we had, let's grab this up right here. Let's grab something nice and straightforward. Okay, this might be an example of a digraph. We would see on here small little arrows. So we could say now that this would be in this direction. Let's put that on. That's not looking like an arrow, is it? Let's make that look like an arrow. That's looking like an arrow. We might have that. We might have, for example, now this. So each of these arcs or edges will have a direction on them. If you want to think about this now, this might model a one-way street system. So here is an example of a directed graph. It's quite rare that these come up in the unit, but it's something that you need to be happy with. So that now is a digraph. It's a directed graph. The next one we're going to look at, which is really quite important, is a tree. A tree is a connected graph with no cycles. Remember, the cycle from before was the closed path. So let's go ahead and look now at a tree. So this is going to be a subgraph of a bigger graph. So let's go ahead now and say that this is graph G. And we could look at an example of a tree. So what we've got then, a tree is a subgraph. So here's the larger graph, and now what I want is the following. So let's go ahead and make a tree. So for example, this could be a tree. That's it. It's as straightforward as that. We've simply now got part of the original graph without any cycles. It's all connected, so we could say now that this is a tree. If we looked at a spanning tree would have to go to every vertex. So if we consider now the following, let's draw a spanning tree. So a tree is simply a subgraph with no cycles. A spanning tree, let's do a spanning tree, right, it's just here. And in your work, you will look at minimum spanning trees. So again, this is really important. If I consider a spanning tree, I might have, for example, this one coming from here to here. I might have that one, I might have this one coming from here to here. As we can see now, all of the vertices are connected. I can't do that. That creates a cycle. That is not a tree. So my spanning tree ensures that each of these nodes are now connected. So a tree is a connected graph. So let's go ahead and look at another one. Quite clearly, these are not exclusive. So we might have more than one spanning tree. So for example, this right here, let's do that. Let's go that way. And you can see I've got a whole host of choices. But as soon as I do that, that is no longer a tree, as there is a cycle, and the cycle is ADC. Okay, let's look now, and what I'll do is what we call a minimum spanning tree. So let's grab this up and put some values on here. And I'll work it backwards to make it slightly easier. Let's say we had now a spanning tree. Let's just draw a spanning tree. So what I'm going to have now is my spanning tree, and I want to make this a minimum spanning tree. A minimum spanning tree is a spanning tree of lowest weight. So let's look at this now. Let's say I've got this scenario. Okay, so I've now connected up all of the vertices. So I might say that, and I'll give these now, let's say that this is the distance in miles between these villages. Let's say that's 1, let's say this is 2, let's say that is 4, and let's say that is going to be 3. What I'd now consider are the lengths now, or the distances of the other one. So let's say this is 7, let's say that's 9, let's say that one's 10, let's say this one is going to be 11, let's say this is going to be 8, and this one is going to be 12. So what I now have is my minimum spanning tree. So minimum, and I'll write it just here, minimum spanning tree. So minimum spanning tree. So let's just confirm what a tree is. A tree now is a connected graph. It's a subgraph of now G in this example, and it has no cycles, so no closed paths. Okay, let's move on and look at what we call a complete graph. So next one, we've got complete graph. Okay, so let me just jot this on. If we look at a complete graph now, and I'll draw some examples. This could be now an example. So what we'd have is this. I could turn this round and we could call this now K3. The terminology that I'm going to use is K3. It has 3 vertices and each vertex is directly connected to the other ones in now the graph. So this would be called K3. It's a complete graph. It's got 3 vertices and now each one is directly connected. So you could probably think of a nice example of this. Let's do now a square or rectangle. This would be an example now if I connected all of these up. Let's go ahead and do that. So if I went from there to there, I went from there to there, I went from there to there, and then finally from there to there. We can see now that this is K4. It's a complete graph. All of the vertices are directly connected to the other, so we could say this is K4. In general, if we have n vertices, it would be Kn. So just consider now, I can go from any one of these. So if I want to, let's say that this is A, let's say this is B, C, and D. From A, I can go directly to B, C, and D. From B, I can go directly to A, C, and D. C, I can go B, A, D, etc., etc. So these are examples now of complete graphs. And we give that now capital K and then now sub n. The next one we're going to look at, and quite an important one, is what we call a bipartite graph. So let's write here bipartite graph. So bipartite graph. Now a bipartite graph has 2 sets, and I'll give you some examples. We might have set X and set Y. So what I'm going to do is just give you an example of this. So what we would have on the left hand side is one set. Now these might be people. On the other side, we might have now chocolates. So what we want to do is essentially link up people to chocolates. We might want to link up workers to tasks. So this is one set, and this set we might call X is the people, and the other set now is Y, and they are the chocolates. So let's say that this was, let's call her Penelope, let's call him Derek, and let's call this one Fred. And then you might have here dark and milk. So Penelope, I think that's what I called her, might decide that she likes now dark chocolate, and now Penelope might also like milk. Derek or David, whoever he was, might only like dark. Fred might only like milk. This is an example of a bipartite graph. You might want to put DA and DE there just to show these are different. Quite clearly, we can match now or allocate or pair up X to Y. We can go from Y to X, but quite clearly, well, unless Penelope wants to eat Fred, we're not going to connect X and X. We're not going to connect Y and Y. So a bipartite graph has now 2 sets. So this is one set of vertices or nodes, and this is the other. We match or pair or look to allocate those in X with those in Y only, and those in Y with those in X only. And these are really quite important. So if we look now at a different example, what I'm going to do is a complete bipartite graph. So what I'm going to have is the following. Let's say, and I'll do this slightly differently, this time I'll put 3 over the other side. Often it really doesn't matter how many I have on each side. What I'm going to have is a complete bipartite graph. So here, let's go ahead and do that. We will do that, and then we will do that. So what I'm doing is simply now connecting all of the nodes in set X to all of the nodes in set Y to make this a complete bipartite graph. So essentially, if these were now workers and these were jobs, this is telling me these 2 workers can do any of these jobs. And we would call this now a complete bipartite graph. Do not connect these 2 up. The 2 workers don't want to do each other. They want to be doing tasks. So let's quickly move on from that. So this is now a complete graph. So complete bipartite graph. And we would say this is K2, 3. So we got 2 vertices on the left and 3 on the right. So complete bipartite graph. And again, it might look something different. You might have 4 on one side, 4 on the other. It really doesn't matter. As long as you have 2 sets and those now are paired up with now the other ones in the other side, it's perfectly fine. So you might have a 4 and a 4. Okay, so an example might be the workers over here can do different tasks or can speak different languages, and you'll be given now some information. So this will be labelled up. Let's say we can send that one there, we can send that one there. But quite clearly we can't send that one there. That is not now a bipartite graph. Now, it's not always the case that bipartite graphs are as obvious as this. They might be the other in some other orientation, but do just check. So, for example, this could be a bipartite graph if now this was actually in this set and they had just done it. So you'd have to make sure that this was actually showing the correct information, and rarely will you be given a different configuration, but essentially you can tell by X going to Y and Y only, and Y going to X and X only, and not now X and X and Y and Y. Let's move on and look at something called isomorphic graphs. Okay, isomorphic just means that they are the same, they just have a different configuration. So all of the same vertices are in there, all of the same connections are in there. So it's the same information, just a different layout. So let me just make one up and we'll see how we go with this. So what I'm going to do is this scenario. Let's grab that up, let's put this one up and spin that round. We'll put that just there, and then we'll go for one like so. Let's do that. And if we do, let's do one more. Let's put this on and connect these two up. So what I might do is have some graph here. So we've got now this graph, and we could label this up. Let's say this is now A. Let's say that's A. Let's say that's B. Let's say that's C, and let's say that's D. So at the moment, we've got this one. Now I could say this is going to be isomorphic to, and then just go ahead and do another one. Let's do something else. Let's grab this up and do something of the same configuration, or at least, no, I should say the same information, just a different layout or configuration. So what we've got then, we'll put that one on there, and then let's do some interesting loops and things. Not loops, just some arcs from here. Let's see what I can do. Let's go for that. And then if I come around and it looks something like so. So when I said loop, not technically correct, as it wouldn't then be the same. And then that. So let's say that this is going to be, what's that going to have to be? That's going to have to be A. This is going to have to be C. This is going to have to be D, and that will be B. So we can say that this graph is isomorphic to this one. It looks different, but essentially it's the same thing. I can see A is connected to C, A is connected to D, A is connected to B. That works. B is connected to A and D, D is connected to A and B, and C is simply connected to A. So we call these now isomorphic. So isomorphic. And as you can imagine, doing them off the top of my head is not the easiest thing in the world, but they rarely come up, but it's something that you need to be comfortable with. Okay, the next thing we're going to look at is what we call an adjacency matrix. This is simply the direct link between two nodes in a graph. So let me draw a graph. Let's go ahead and draw another graph, and what we'll do is now an adjacency matrix. So let's say we've got this, and then I'll do another one. Let's put up another one here, and as I'm kind of thinking as I'm going on this, but we'll just label these up. We might have something like that. We might have something like so. And then I'm going to put a loop on this as well. So let's say we got a loop just here. Okay, loop just here. And now let's say we can put now another arc between these two. So let's put another arc between those. Okay, let's put some on. Let's say this is going to be A. Let's say that's going to be B. Let's say we'll go for this one C. Generally, I'll go for that one as C. And D. So let's now draw an adjacency matrix. So what we've got then now are the direct connections between the two. So we'll have A, B, C, and D. Often yours will be bigger than this, but as I'm kind of making it up as I go, I'll keep it nice and sort of minimal. Okay, so here we've got now A. So let's put A. We've got B. We've got C, and we've got D. We've got A, B, C, and D. So if we consider now the ways that we can get from A to A, the answer is none. Okay, and instead of putting a dash through here, put none, and you'll see why shortly. Okay, if we look at A to B, Now, A to B, I could go this way or I could go this way. So what I'm going to do is state that there are two ways to get from A to B. Now, if that's 2, then that's 2. And we'll notice with this, it's going to be symmetric about this diagonal. Okay, let's look at A to C. Well, A to C, there's just one direct connection. So A to C, A to C. If we look now at A to D, we've got 0. So A to D, D to A, 0. If we look at B to B, we've got 0. If we look now at B to C, we've got 0. So we can't go directly from B to C. So we're going to put 0 and 0 just here. Let's now look at C to C. With C, now I can go this way round, or I can go that way round. Therefore, in now the adjacency matrix, we have 2. So 2 ways to get from C to C. And now if we look at B to D, there is 1 way, so we can now put in 1 just here. If we go from C to D, we can see there's 1 way, and we can go from there to there. If we look now at D to D, that's going to be 0. So this now is called an adjacency. So adjacency, let's write that there, adjacency matrix. So matrix. And that's all we're doing is looking at the different ways we can get from one vertex to the next. Okay, let's look at another one. Let's look at what we call a distance matrix. So let's look at distance matrix. Okay, I'm trying to remember this as I'm going, so bear with me on it. I'm kind of winging it a little, but hopefully it'll make some sort of sense. So let's do this scenario. Let's go for, let's just, nice and straightforward, we'll just draw something a bit easier. So let's say we've got, I don't know, let's go for a rectangle. Okay, so here's my rectangle, and then I'll put up now one just here, okay, and we'll put that one just there. So let's say we've got A, B, C, and D again. So let's go A, B, C, and D. So here's A, here's B, here's C, and here's D. Let's put some values on. Let's say we'll go 4, 5, let's go 6 down the middle, let's go 3, and then we'll go 2. Now remember, despite this looking the same distance or the same weight, whether that's time, whether it's cost, the network, if we had one, or the graph, the actual weight does not always correspond to the length. So as you'll see, sometimes when you say which is the quickest way to get, for example, from B to D, if this now was 15, then we can see it would be B to C and then C to D, or the other way, B to A and A to D, rather now than going across here. So you can see it's exactly the same distance or weight there. So let's go ahead and draw now up a distance matrix. So I'm going to get my distance matrix, and it looks something like so. So we'll have that, then we need 4 just here. So what we're going to do is just place these in and just write them up. So now we're looking at the distance. Let's say that this is kilometres between towns. So A, B, C, D. I think it's also important to stress that this isn't necessarily saying that these towns are perfectly in some kind of rectangle. This is just representing the arcs or the sort of journeys between them, rather than being looking physically like this. Okay, so let's think about this now. A to A, quite clearly, well, the distance is going to be 0. So nothing for A to A. And as you can imagine, going down the diagonal now, we're going to have in here, all of these will now be nothing. The reason is because there's no loops. If there were loops, or different now, well, I should say rather than loops, if there were different ways that we could get to it now, if I had another arc here, then we'd have to consider the case where we had an alternative way from A to B or A to D. So if we look at A to B is 4, B to A is going to be 4. Okay, if we look now at A to C on here, looking across, we don't have a direct route. So straight off, we're just put in here, no direct route. Okay, again, you could argue that 0 goes in here. Different definitions will have different things. I would say the dashes would suffice. Okay, let's look at D to A. A to D, that's going to be 2. A to D is going to be 2. Okay, let's look at now B. B to C, we've got 5, so we've got that one just there. B to D, we can see that's going to be 6, so we can put that there. C to D, that's going to be 3, and then we're going to have 3 just here. So this is now a distance matrix. So all we've done is simply put now the distance between the two. Now this might alter, so let's look at a case of where we might alter this and go over and look at one. So what I'm going to do, let's grab up, let's have a play about with these. I'm going to get that one, and then what I'll do is get this one and spin it round. We will have now, let's say we've got something now where we go, let's do this, let's go there, and then let's put now on an alternative. So what we'll have is something like so. So let's say that this is going to be, let's call this A, let's just say this is A, this is B, and this is going to be C. So it looks like we've got some kind of wonky ice cream at the moment. Let's say that we put on here 5, let's say we put on here 4, let's say we had 2, and let's say we had 3. Okay, now with this, quite clearly we can see there's 2 routes, and when you think about modelling this up in reality, that's feasible. So for example, this might be the motorway, this might be the country road. So let's go ahead and do this one. So we've got now 3 of these to consider, and it'll look something like so. Then we've got 3, so let's put that one there, and then that one there. So this is now going to be a distance matrix, but we've got a slightly different scenario. So let's now put A, B, C, and then A, B, and C. And this one will not now be symmetric. So if we consider A to A, again, nothing is going in there. B to B, we've got nothing in there. C to C, got nothing in there. Now, if I look at A to B, what I can say is A to B is going to be 4. But in this one now, I'm going to go this way and do B to A, which is going to now give me 5. So that's going to be 5. A to C is 2 and 2. If we look now at B to C, 3 and 3. So in that particular case, bit off the top of my head, but you can see now it's not symmetric as we got 2 choices from A to B. Okay, so that now is another example of a distance matrix. We're now going to move on and look at something very slightly different. This is picked up in another tutorial looking at the shortest distance. And what we're going to look at now is the following. We're going to look at what we call Eulerian or Eulerian graphs, depending on how you pronounce it. I prefer Eulerian, but again, it's entirely up to the person who is saying it on how they pronounce it. Okay, let's first look at an Eulerian graph, and I'm going to draw one up. Now, an Eulerian graph is what we call fully traversable. So let's go ahead and do that. In fact, I'll just draw it from here. So let's grab up that one, and let's grab up this one. So I'm going to have now here, and I'll connect all of these up. We're going to have something that looks like this. Now that goes across there, that goes across there, that'll come down here, that'll go there, then we'll have that one come in here, and then we'll have that one go in there, and then finally we'll have that one going there. What I'm going to do is go around this and look now at the nodes themselves. We're going to look at the valency, the order, or the degree of the nodes. So this has now 2, this one has 4, this one has 4, this one has 2, this one has 4, this one has 4. If this is Eulerian, now the valency of each will be even. So this is called Eulerian. So we have now even valency or even degree. This is what we call now fully traversable. We can start now, let's pick a point, let's start anywhere we like. We can start here and simply now go right the way around this without taking our pen off the paper. So if I consider now, I can go round, I can go round, I can go this way, and I'm not now going to repeat any of these. So all I'm doing is simply going round. I don't have to take my pen off the paper to do this. Okay, then I'll come round, back up there, and I'll end up back at the start. So this now is called fully traversable, and that now is one of the features of an Eulerian graph. An Eulerian graph has all even valency. So that's an Eulerian graph. Let's look at what we would call a semi-Eulerian graph. A semi-Eulerian graph, so let's go ahead and draw one. Let's go and do, let's see, grab that up, okay, and we'll move it into place. Now with a semi-Eulerian graph, we have a maximum of 2 odd nodes. Now remember from before, odd nodes will appear in pairs. So what I'm going to have is this. Let's go ahead and now put this on. So I'm going to start connecting up now my graph. and then we'll come, let's go across that way, let's come back down that way, let's go up here, and then let's go down here. So if I now look at the valency, or the order, or the degree of these nodes, I've got 2 here, I've got 4, I've got 2, I've got 3, and I've got 3. So we can say that this is semi-Eulerian or semi-Eulerian, however you wish. Now this has a maximum of 2 odd nodes, and it's exactly 2 odd nodes. Quite clearly we can't have now 0. Oh, well, we can have 0, we can't have 1. We can't have 1 because now if we've got 1, we must have the other, as now the sum of the valency is always going to be an even number, and we saw that with the handshaking lemma. Now with this particular case, what I can do, and I'll do this with the pen again, I can start now at one of the odd nodes. So if I start at one of the odd nodes, I can go round this like so, come back up this way, across here and back, but I must finish at the other odd node. And this is called semi-traversable. So I start at one odd node and I finish at the other. To make this Eulerian, we must now repeat the arc between the 2 odd nodes. So if I wanted to now make this fully traversable or Eulerian, I'd need to repeat that. So what I'd have to do is come up here. Now often we represent this with a new arc. This doesn't mean we go ahead and build a new road or canal between the 2. It's just saying that we're going to now make this traversable. If we wanted to start and end at the same node, we'd have to repeat now the arc between the 2 odd nodes. So semi-traversable, semi-Eulerian, we can now start and finish at either of the odd nodes. So that's what we have. Now the other scenario is it's neither Eulerian nor is it semi-Eulerian. So it's got now, for example, let's draw something like so. So let's go ahead and have a go at one. Let's grab up, what do I want? Let's do it just here. Let's say we had this now. So with this now, what I'm going to do is a graph that's neither Eulerian nor semi-Eulerian. And you'll see that I won't be able to go right the way around without taking my pen off the paper. So if we look at this now, we've got that scenario. So I can see now on here, let's do that one and then I'll do it. So what we've got now is the valency of each of these is going to be 3, 3, 3, 3. Okay, if I tried to do this one, let's go ahead and do this one. Let's say we wanted to start there. Let's come up here. Let's come down here. Let's come down here and let's go up here. I'm now trapped. I needed to do that one and I can't do it. So this is neither Eulerian nor is it semi-Eulerian, as we've got more than 2 odd nodes. Eulerian has none, semi-Eulerian has 2 at most, and then the one that isn't has neither. So what we've got then is this example, and a problem that you might have seen in the past is something called the bridges of Königsberg, and it's one of those little puzzles that you do, and it's based on this idea. So if you created an additional arc, you could make it either semi-Eulerian or Eulerian depending on how many odd nodes that you had. So there we go. I'm kind of getting a little tired, but hopefully that's been a good introduction to graph theory. I think what I'm going to do for the next minute or so is say some words. If you want to hit pause or give yourself 5 seconds to try and do them and come up with a definition. We'll see how it goes and then you can decide whether you want to use that. So, for example, if I said spanning tree. A spanning tree is a subgraph with all now of the vertices in the original graph. As it's a tree, it can't have any cycles. So connected graph, a subgraph now with all of the vertices of the original graph. If I said simple graph will have no loops, and with the arcs, we can't have now more than one arc connecting any 2 vertices. An adjacency matrix, that gives us now the number of direct links between 2 vertices. Bipartite graph has 2 sets, x and y. X can go to y can go to x, but x can't go to x and y can't go to y. Complete graph, all of the nodes or vertices in the graph are directly connected to the others. If we look now at a path is a finite sequence of edges that start and end a vertex, and a vertex, any one vertex, cannot now be visited more than once. Subgraph is part of an original graph, so it might just be simply two of the arcs connected up. Isomorphic graphs show exactly the same information, they just have a different configuration. Okay, a loop now is an arc that goes from one vertex back to the same vertex. A graph is just a collection of nodes or vertices and arcs or edges. A cycle is a closed path. A tree doesn't have a cycle in. A tree now will ensure that it's connected, it will be a subgraph, but it doesn't have any cycles in. I think that's me just about done. I think we'll chuck in one more, trying to remember another one. Digraph. Digraph is simply now a directed graph. So we'll have the arrows saying which way we can go along the edges. So there we go, 45 or so minutes looking at basic graph theory for decision maths. Hopefully I've crammed everything in. If not, leave me a little message to tell me what I need to add.